Welcome to this lecture on remote sensing. This is an introductory lecture, taking up some very basic concepts that we need when we're using remote sensing as a tool for gathering in data on the state of the Earth, the Earth's surface of the Earth, or even its atmosphere. But this lecture will focus on looking at the surface of the Earth and what exists there. So remote sensing, the name implies, as it says here, no direct contact with the ground. It's remote. So we don't actually measure by contact anything. We are looking at some other thing that is being given off by the things that we want to measure. Usually this means electromagnetic radiation, which is light. We think of electromagnetic radiation as a spectrum. Going from, we have radio waves there, they are electromagnetic radiation, light, infrared, all of these things are electromagnetic radiation. They are essentially the same thing, just with different energies. Another alternative remote sensing quality that we could, or another quality we can measure remotely is gravity, which doesn't belong to the electromagnetic spectrum. For example, GRACE, the GRACE program measured gravity. We won't be looking at that in this lecture. That's for somebody else. In this, we will simply look at electromagnetic radiation. And we can also divide remote sensing into a couple of other categories. We can look at passive or active remote sensing. Passive remote sensing is perhaps the most common, or at least has been, and it's certainly what we are going to be looking at here. So we're looking at naturally occurring light. The sun illuminates the Earth, and that light is reflected back and then picked up by our sensor, our camera. We have active sensors, active remote sensing, in which we send a signal out. We have some sort of instrument that emits a signal, and that is then reflected back. For example, LiDAR or radar measurements. We can also be ground-based, aerial, or space-based. So if we're standing on the ground, if we have ourselves are in contact with the ground, but our instrument is on a tripod, for example, and we're taking pictures or doing a laser scanning, for example. We may be up in an aircraft, a drone, a helicopter, more commonly an aeroplane for remote sensing, certainly traditionally it has been this, or in a satellite orbiting in space. We have some data gathered, LiDAR data gathered from, say, the space shuttle. But most commonly we're talking about satellites. And the data, what does it look like? If we're talking about reflected light within the visible and near infrared ranges, we might end up with images like this. So on the left we have Oslo, shown essentially a true color image, RGB, and on the right we have a near infrared image, commonly used for vegetation mapping, and that's over the Po Valley in Italy. Just to exemplify what we're talking about, the sort of things, you've probably seen something like this before, you definitely have on this course at least, but this is what we're talking about. So to go over that again with the two main categories that we will be taking up within, certainly on this course, aerial photography and satellite imaging. I'm going to talk a little bit about aerial photography, but not very much, just to get some basics in. Mostly we won't be focusing on satellite imaging, but a lot of what applies to one applies to the other. Not always, but quite a lot of it does. So as previously mentioned, aerial photography is usually done from aeroplanes, at least for the high quality data that we're talking about here, with a camera that's looking straight down on the ground. And we're capturing a photograph. That's what it is. We're taking an image over a large area, and it's instantaneous. One image, and then another image, and then another image, a sequence of images. Whereas in our satellite-based imaging, we have a sensor that is usually pointing straight down. In most cases it does. Some sensors are capable of being turned to the side to get to look at something off orbit, so to speak, so that, or off the path rather, so that we can re-look at something that that the satellite isn't directly over. This improves the temporal resolution. And the satellite-based methods, quite often we're talking about capturing, rather than an image over an entire area, it's capturing a sequence of data, usually a strip, or across that stretches across the orbit path, and then we just capture row by row of data. So for the aerial photographs, we're in an aeroplane looking down, taking a sequence of photographs. So our aeroplane is flying overhead, and it takes a picture and another picture and another picture and another picture and another picture, turns around and then recovers an overlapping area. As we can see, we have this overlap, and this is not just to make sure that we've captured everything, that we've not missed an area, but also to aid interpretation and calculate elevation of objects within the image. We need to know where the aeroplane is, where our sensor is positioned, and for that we'll quite often use, at least nowadays, GNSS to position the aircraft so that we know we have an accurate position of for the center of the image. And then we need to position the rest of the image as well, using various methods. But the overlap is more specifically used for calculating the height of objects within the image, amongst other things. And we can see that we can calculate the scale of the image. So this tells us not only how large an object we can see in the image, but also the resolution of the image for when we're doing our mapping further on. When we're taking this image and turning it into a map, what can we actually say about what's in the image? What's the smallest object we can find there? So this is quite important information, and it's directly related, at least the scale at the nominal ground level, we can calculate. Obviously, we have changes in elevation, which is going to make things different. So the size of something will change. Its apparent size in the image will change due to its relative elevation within the image. So if we calculate our scale down here at sea level or ground level here, something sticking up is actually going to have a slightly different scale in the image. That's something we need to deal with as well, but using geometry to sort this out. And one of the things that that aid us in this is the parallax effect, whereby something higher up becomes shifted, apparently shifted in the image. If we see here, we have a tower block of some sort of tower in our image, and the point on the ground, seen from our aircraft, that seems to be at the correct location, but the same point, the same location at a higher elevation, due to this parallax effect, we end up with that being pushed over somewhat because of the light rays passing through this focus. We end up with this distortion, rather than having straight lines of light coming towards us. Everything gets focused through a lens. With the satellite-based methods, rather than capturing this image, again, we're capturing a strip of data, generally speaking. And this film sequence here from the European Space Agency is illustrating that, also illustrating that we're capturing lots of different colors in a satellite image. With aerial images, we tend to only capture 3 or 4 different colors, blue, green, red, and near infrared, whereas satellites, perhaps due to the greater expense of putting a satellite into space, it might as well just invest a little bit more money and put more sensors in there. Perhaps makes more sense. We could capture more data from an aircraft as well, but it's not deemed necessary. But where are these satellites? Where are they in space? I mean, apart from around the Earth. We have different names for different types of orbits, but generally speaking, we are, with our remote sensing data, we are quite often using this low Earth orbit, and usually at the lower end of this as well, rather than higher up. Interesting for us as well here is the polar orbit, whereby our satellite passes over the poles, which allows the Earth to rotate underneath the satellite's orbit, which enables the satellite to pass over every part of the Earth at some point in its during several orbits. This will be illustrated soon. But also, generally speaking, we want to revisit the same place at the same time of day with the same illumination in order to make the images comparable. So we tend to have a polar sun synchronous orbit for a lot of these remote sensing satellites, at least for the ones that work mostly in the visible and near infrared ranges. So this is again another sequence from the European Space Agency illustrating how Sentinel-2 orbits the Earth, and as we can see, it captures a strip of data, and the Earth passes underneath it as the satellite orbits around the poles here. It captures strip after strip. Because the Earth is rotating beneath it, it can, in the end, cover the entire globe. It takes several orbits to do this, and as we can see here, 5 days for the pair of satellites to capture all the data of the entire Earth. Sentinel-2 isn't the only satellite out there. These satellites, the Landsat, is the oldest set of satellites. Landsat 9 was launched recently last year, but Landsat dates all the way back to 1972. The first Landsat wasn't actually called Landsat at the time, but was launched on the 23rd of July 1972. And there's been a Landsat operative continuously since then. So there is quite a database to go back to. Obviously, the resolution in the early satellites wasn't as good as we would get nowadays, and the program has expanded in the different types of light that it's capturing. But Landsat is the baseline, we can say, for what everything else can be measured against. Sentinel-2, indeed, which is a much more recent program, definitely tried to make itself compatible with the Landsat data, so that you can do a time series of images and look at those and do change detection using both sets of data. It's not straightforward, but it is perfectly doable. And then we have things like SPOT as well, another European project where we're gathering data in. SPOT is not always freely available. Landsat and Sentinel are free to use. You need to register, but apart from that, you can go and download data from the Landsat program or from Sentinel-2. In fact, Sentinel, the European Space Agency program, it's called Sentinel-2 there. Sentinel-1 is radar. Sentinel-3 is also radar. There's a whole range of programs, Sentinels 1, 2, 3, 4, 5, so on, covering different aspects of Earth observation. I think we can say that we've covered that now. The ones on the screen are based on visible light and near infrared. Generally speaking, freely available or almost freely available, with a spatial resolution or ground sampling distance, however we want to describe this, in the sort of tens of meters, 10 to 30 meters, generally speaking.